also has like a one of these kind of antennas. And then let's let the third house be just really weird and have multiple windows. Boarded up. Okay, good. Okay, these are my 3 houses. And there are 3 public utilities which we'd like to connect the houses to. This is electricity, this is gas, and this is telephone. It is like a puzzle. Is it possible to connect each of these houses to each of these 3 utilities in a way that the lines don't cross?
No, there's a way.
There's a way?
Isn't it? I feel like it was in puzzle books.
Yeah.
I don't know what kind of puzzle books you're using, but if you have 3 houses,
I don't know, but it's
and okay, so if you have 3 houses and you're doing it all like on a level, how should we say this? Yeah. Okay, so how can I do this? Well, I can connect electricity to each of the 3, but now I'm stuck, right? Because how do I connect gas to the 3 houses without crossing any of the electricity lines? Okay, well I can do this. So, and I can do that, and I can do that. I probably should have used colors. But now, that was fun. No? Go the other way, says you.
yeah.
Like that?
Yeah.
Okay. But now we have problems. Can I connect telephone to house 2? Yes. Can I connect telephone to house 3? Yes. Can I get from the telephone, even with curly lines, to house 1? I simply just can't. Okay? So this problem cannot be solved. In fact, that was pretty much, would you like a formal proof of this? Okay, the formal proof of this is basically the same damn thing. So theorem K33 is not planar. Am I still in window? Frame?
Yeah.
Okay. Okay. Theorem K33 is not planar. Okay, what is K33? K33 is this graph. It's the graph ABC, and then there's DEF. It is the complete bipartite graph of order 3. A is connected to each of these. Okay, well this time I'm not even trying, right? I'm just drawing it. So the vocab here is that we say this particular embedding is not planar. But that doesn't mean that just because a particular embedding is not planar, that doesn't mean that there is no planar embedding. Because as we've seen over here, this was a non-planar embedding, but this was a planar embedding. So we say a graph is planar if there is a planar embedding. Okay, but my theorem is that there just is not one, and so the graph is not planar. Why? Well, basically you just kind of try to brute force it out, and then you just argue that it can't be done. So let's first take 4 of the vertices. Take A, where'd E go? Take A, E, B, D. Okay, so take 4 of the vertices. A, E, B, and D. Is it possible to make a planar embedding of that subgraph? Yes, it is, right? Here is A, E, A, B, and B, E. This subgraph has a planar embedding. And what must that planar embedding look like? We have to take it and go, so we can put A here, and E here, and then I guess B would be down here, and D would be down here. Alright, so if we do this, A is connected to E, E is connected to B. This is pretty similar to what we just did. A is connected to D, and B is connected to D. So that's what we have so far. Okay, now the question becomes, I have to now add in C and F. Well, note that by connecting these 4 vertices, I now have created 2 regions. The regions are, let's call this first region like R1. R1 is the geometric region inside this square, or whatever, quadrilateral, and R2 is the region outside the square. And so now I have to put, take vertex C for example. Where can I put C? Well, as region 1 and region 2 exhaust the entire plane, Sage, I have to put C in one of those places. Where do you want to put C? What? Yeah, stop sleeping, wake up. Where should C go? Someone.
Outside.
Okay, he says outside. So case 1, let's place C in region 2. Well, if we place C in region 2, then the picture looks like this, right? Here's A, here's E, here's D, here's B. D, A, E, and we have the C outside. Well, if we place C outside, what is C connected to? C is connected to D. Okay, that's fine. C is connected to E. That's fine. And C is connected to, wait, B. No, F. Where the hell is F?
We have to add it.
Oh, yeah, good. We have to add F now. C is connected to,
Wait,
wait, I think I did something wrong.
I think there's more cases than this.
No. No. Now I have to put F somewhere. Okay, actually, maybe I should just do this. Well,
Shouldn't you draw a picture of C is on the other side of
I
the
think
square?
no. I think I need to decide whether to put F also in region 2 or in region 1.
Okay.
I think that's what matters, right? So if I put C in,
No.
yeah. Where do I put F? If I put F, I'm forced to put F outside.
Because otherwise it crosses into.
Yeah, F cannot be in region 1, otherwise I will cross one of these edges on the way in. So F must be out here in region 2 somewhere. But now we're screwed, right? Because C has to connect to D, E, and F. But if it connects to E and F and also D, now F cannot connect to B. It's just impossible. It can't be done. And the same thing happens if we try to put C in the middle. If case 2 is we try to put C in region 1, well, if we try to put C in region 1, then we have A, E, B, and D. Zon, 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 zon. Well, let's try to put C in the middle. Well, if we put C in the middle, where do we have to put F? We have to put F in the middle too. Because F can't go on the outside, otherwise the line connecting C and F would cross through one of these things. So we have to put F, say, somewhere in the middle with C. But now, C is connected to D, E, and F, which is fine. But then F has to connect to A and B, and it can connect to B, but C simply cannot connect to A.
Or it could be on the other side and not connected.
Or it could connect to, or it could be, F could be here. This is what Gabe is saying about extra cases. Yeah. Okay, but it basically just can't be done. Okay, cool. Okay, well it turns out that K33 is not just some random graph which is not planar, but it is like one of the fundamental building blocks of non-planarity. The other one being K5. So other theorem, K5 is not planar. And this is something which seems sort of obvious that it's not planar, so I can just draw K5, right? 1, 2, 3, 4, 5. K5 is just the complete graph of order 5. And like, dude, there's just going to be no way to draw that in a planar way without the edges crossing each other. Just forget about it. Okay, but actually proving this is hard. So okay, proof, or let's just say medium hard. And there's a homework problem which just like walks you through this proof. So you're going to do that for homework and we'll go over it next class. But you will soon prove, although it's not totally obvious how to do it, that K5 is not planar. What's interesting is that every single non-planar graph is effectively built out of K33 and K5 in a certain kind of way. And a certain kind of way is a little bit hard to explain, but more or less, Gauss introduces this concept of a homeomorphism, which is a general thing that probably Schwartz taught you already. But if not, we say that two graphs are homeomorphic if they are each descendants of another graph, which was created by removing elementary subdivisions. Okay, what the hell am I talking about? Well, suppose I have a graph, A, B, C, D. And now, suppose this graph also has a bunch of little like bumps along the way, like whoop, and like whoop, and like let's put another one here. Do you sort of like feel in a certain way that like these little dots, which are not doing really anything, are kind of like not important to the overall structure and do not affect planarity? I feel that way. Okay, so this is what's called an elementary subdivision of an edge. An elementary subdivision of edge AD is a vertex which cuts AD into two edges, one being AE and one being ED. And I could just like get rid of vertex E and like not really change anything. So if you have a graph and you cut it up, it is possible by removing elementary subdivisions to turn the graph into any other kind of graph. So let's like take out some of these things that don't belong. So like, I don't know, I'll leave E there, but I'll take out like, actually let's be kind of cool. Let's take out B. Just, that's probably not what you were expecting, so that's a little bit exciting. And then that's it. Good. Alternatively, I could take out maybe like all the other points. Okay, so these two graphs are called homeomorphic. They are homeomorphic because both can be derived from a common ancestor using only a sequence of elementary subdivisions. Yo.
What about?
Actually, I think I really what I want to do is actually go the other way. Well, anyway.
What about
Yeah.
triangles where you can't take anything off, but it doesn't feel much different from other polygon-like graphs? Like triangles.
What about triangles?
Like triangles, I would say don't have any elementary subdivisions because if you take it
Okay.
off, it's a line.
Yeah.
But a triangle doesn't seem much different from something that would have elementary subdivisions. So how do you?
Okay, wait, hold on. So basically, the theorem is called Kurotowski's theorem, and Kurotowski's theorem says that every single non-planar graph has a subgraph which is homeomorphic to K33 or K5. Every non-planar graph has a subgraph which is a homeomorphic to K33 or K5. Okay. Example. Are you like doing anything? What are you doing? Yeah, can you take out a piece of paper and like follow along? Okay. For example, take, I will give you some kind of crazy graph. It looks like this. Actually. Here, I'll just like make one up. No, that's better. So we have B, A, F. Should we do this on the computer? It's a little bit more fun. Okay, let's go over to the computer. Do you want me to turn the lights off and you guys just watch the screen, or do you want to huddle around? Let's huddle around. That's more
Can
fun.
we do the projection?
No, projection.
No, because then you're all just going to fall asleep. I hate you, I hate seniors, I hate students, and I hate teenagers. Everyone, shut up, stop whining, stand up, get over here.
That was very.
I didn't see like some of the coolest stuff in the whole semester, and you're all just like, ooh. Yeah, good. I got put in this class and guess what? It's all coming out.
Just running.
Sage.
No, my constitution. Whatever. Wait.
Sorry, Sage. I'm
glad
sorry.
I'm in your class.
I'm sorry that I'm giving you an education.
There's only 11 minutes of battery left.
Good. Turn that off. Actually.